What if I told you we're trying to build a star right here on Earth? I'm talking about a source of clean, almost limitless power. For decades, that's been the dream. But the incredible machines we built to do it, well, they're hiding a pretty big secret. They're leaking energy at a rate that shouldn't be possible, and we're going to dive into why.
It all starts with a simple and, frankly, kind of scary fact from physicist Leslie Woods. Our need for energy is just exploding. It's growing exponentially. And with fossil fuels on their way out, the race is on to find a replacement, something clean, powerful, and pretty much inexhaustible.
And that's where nuclear fusion comes in. It is literally the same process that powers our sun. If we can fuse light elements together here on Earth, we could unlock an energy source that's clean, incredibly safe, and get this, uses fuel that's abundant in ordinary seawater. I mean, it's the ultimate energy dream, right?
But, dreaming about it is one thing. Actually building it is a whole other ballgame. The challenge is just staggering. How do you possibly recreate the conditions you find at the heart of a star? And then, once you've made that little star, how in the world do you contain it?
Okay, so let's get right to the core of the problem, the thing that's been puzzling scientists for more than half a century. It turns out that the bottle we've built to hold our star, well, it has a leak, a really, really big one.
To get fusion going, you need some serious heat. I'm talking temperatures that make the sun's core look kind of lukewarm. We need to get over 200 million degrees Celsius. Let that sink in for a second. That's more than 12 times hotter than the center of the sun.
And at these insane temperatures, obviously no physical container can hold the reaction. It would just instantly vaporize. Matter itself actually transforms into a fourth state, a swirling, superheated soup of electrically charged particles we call a plasma.
The only thing that can possibly contain this plasma is an incredibly powerful magnetic field. Think of it like an invisible thermos that, in theory, should trap the heat almost perfectly. Reaching ignition should have been, well, not easy, but straightforward. But reality had other plans. The heat escapes at a shocking rate. Our magnetic bottle is leaking, and for decades we haven't been totally sure why.
So let's take a closer look inside that magnetic bottle. We're going to explore the incredible machine at the heart of this entire mystery, the Tokamak.
It's called the Tokamak. It's a Russian acronym, stands for Toroidal Chamber with Magnetic Coils. This donut-shaped design was first cooked up in the Soviet Union way back in the 1950s, and it's still the leading contender in the global race for fusion energy today.
And this is what one of them looks like in the real world. This beast is the Joint European Torus, or JET, over in the UK. Just get a load of the scale of that thing. This isn't some tabletop experiment in a lab. It's a massive, unbelievably intricate piece of engineering designed to do one thing: tame the power of a star.
So, how on earth does it work? Well, it's kind of like a three-step dance of physics. First, you heat a gas until it becomes a plasma. Simple enough. Second, you squeeze it. Massive coils wrap around the donut, creating a powerful magnetic field that shoves the plasma away from the walls. And third, you control it. You induce a powerful electrical current inside the plasma itself, which generates a second magnetic field that twists and stabilizes the whole shebang.
The whole point of this incredibly complex machine is to achieve one critical milestone. We call it fusion ignition. But what does that actually mean in terms of physics? Okay, this graph right here, this is the ignition curve. You can basically think of it as the recipe for a self-sustaining star. On the bottom, you've got temperature, and on the side, a measure of how well the plasma is being contained. The goal is to get the plasma conditions into that perfect sweet spot, right at the bottom of the curve, the fusion reactor zone. That's the point where the fusion reactions start producing enough energy to keep the plasma hot all by themselves.
To get into that zone, you've got to master three things at once. It's what scientists call the triple product. You need extreme temperature, you need a high enough particle density, and you need a long enough energy confinement time. And that last one, that's the kicker. It's all about how long you can hold on to the heat before it leaks out.
The target number for that triple product is just immense. It's greater than 5 times 10 to the 21st. Hitting this number is the scientific equivalent of a grand slam. And we've come so close, but that leaky bottle problem, that confinement time, that's what's been holding us back.
So let's get back to our mystery. Let's reframe this, not as a physics equation, but as a crime scene. Let's call it the Great Energy Heist. Who's the culprit stealing all this energy? The scale of this heist is just staggering. Based on our simplest theories, the energy loss should be tiny, but what we actually see in experiments is a loss rate 100,000 times greater. Something is siphoning heat out of the plasma at a rate that just flat out defies our classical understanding of physics. Now, in the source material for this explainer, the physicist Leslie Woods points to a potential culprit that he argues has been totally overlooked. He claims there's a known physical process out there that could explain this massive energy loss, but that it's just ignored in most of the scientific literature.
Wood's theory points to two effects working together in secret. First, imagine the plasma spinning like a layered cake. Fluid shear is basically the friction between those layers as they rotate at different speeds. Second, you have transverse heat flux, which is a fancy way of saying heat is getting pushed sideways across the magnetic field lines when it shouldn't be. Woods argues these two forces combine to create a hidden drain, a secret escape hatch that's funneling enormous amounts of energy right out of the system.
So, whether Wood's theory is the final answer or not, the hunt for a solution is on. All around the world, the scientific community is building bigger, more powerful machines to finally crack this puzzle once and all.
And the next great step in this quest is ITER, the International Thermonuclear Experimental Reactor. It's being built in France, and it is one of the most ambitious science projects in human history. It's a global collaboration with a goal that's absolutely monumental: produce 10 times more energy from fusion than is put in to get it started.
And the success of this multi-billion-dollar machine, it hinges entirely on correctly understanding and predicting this very same mysterious energy loss. Getting the physics of that leaky bottle right isn't just an academic question anymore. It's the foundation our entire energy future is being built on.
Which leaves us with the ultimate question, doesn't it? For over 70 years, we've been on this quest. We know the destination, limitless clean energy. We have the map, that ignition curve, and we have the vehicle, the Tokamak. Is figuring out how to finally plug the leaks in our magnetic bottle the last great puzzle we need to solve to bring the power of a star down to Earth?